Good morning. In this video, we are going to discuss the stereochemistry in metal complexes. You may be very familiar with stereochemistry in organic compounds. Before we go into this topic, let us recall the basic definitions in stereochemistry. First one, stereoisomerism. In this, the molecule will have same atom-atom bond, but their orientation in the space will be different. This property is referred as stereoisomerism. The next definition is chirality or chiral compounds. The direct meaning of chirality is handedness. It is not possible to superimpose the right hand over the left hand. Similarly, for few molecules, for chiral molecules, it is not possible to superimpose the mirror image with the original molecule. That property is referred as chirality. Basically, it is non-superimposability. Generally, this property is achieved when the molecule has 4 different groups or atoms attached to a carbon. For example, let us consider a carbon with 4 different groups or atoms. This one cannot be superimposed with the mirror image. The mirror image will be like this. These two are non-superimposable and this carbon is referred as chiral carbon. Generally, to find out the chirality, we look for plane of symmetry. It is easy to find out the plane of symmetry. If it is absent, then the molecule will be chiral. In fact, we have to look for inversion center. In terms of improper axis of symmetry, I is equal to S2. So when I or inversion center, when these two are absent, that time the molecule will be optically active, that will be chiral. What do you mean by optical activity? It is nothing but the ability to rotate the plane polarized light. The plane polarized light will be rotated in the clockwise direction or anti-clockwise direction. One stereoisomer will rotate the plane polarized light in the clockwise direction. Its mirror image will rotate the plane polarized light in the anti-clockwise direction. So these two stereoisomers are referred as enantiomers. Stereoisomers that are mirror images are referred as enantiomers. This molecule is mirror image of this. So these two are enantiomers. The next one is diastereomers. Stereoisomers which are not mirror images are referred as diastereomers. Now let us discuss the stereochemistry in metal complexes. Often we come across tetrahedral and octahedral complexes. Let us consider a tetrahedral complex like this. Imagine 4 different ligands are attached to the metal. The geometry is tetrahedral. This is similar to chiral carbon. Instead of carbon, I have metal. Both are tetrahedral in shape. So we can expect this molecule or this complex to be optically active. But this type of compounds are very rare. The complex will be labile. Because of that, it is not possible to isolate this kind of complex. Even though theoretically it is possible to get optical activity for this kind of compound, it is very difficult to isolate such complexes. On the other hand, it is possible to have chiral octahedral complexes. It is not compulsory that all the 6 ligands should be different. Let's consider a complex like this. Here I have 4 ligands A, B, C and D. Let us consider the mirror image. It will be like this. Sorry, these two structures are superimposable, so I modify this little bit. Let us consider E here. In this case, it is not possible to superimpose the mirror image with the actual molecule. So this molecule will be optically active. It can rotate the plane polarized light. I go for one more example. Here I have only 3 ligands. The mirror image will be like this. These two are not superimposable. So when you have minimum 3 ligands and when they are placed in this fashion, that complex will be optically active, that can rotate the plane polarized light. First we are going to discuss Baylor's method. Using this, we are going to predict the total number of possible stereoisomers. Let us consider a metal complex like this. Metal with 6 different ligands. What will be the total number of stereoisomers in this case? First I am going to take A, ligand A. Opposite to that I can have B or C, D, E and F. So I am going to get 5 rows now. Opposite to A, I can have B, I can have C, D, E and F. When I have B opposite to A, I have 4 more ligands. The 4 more ligands can be placed in 3 different ways. So I am going to get 3 columns. AB already I have taken. So now I have CD and EF. So I place them like this. The next one I place CF and DE. Here F is opposite to C, E is opposite to D. The other possibility is CE and DF. Similarly, let us consider the next one. AC I have taken. The remaining ligands are BD and EF. I go for cross ligands like this. ED. Next one BE and DF. The next possibility AD. Then I am left with BC and EF. Next one AE. Finally, we are left with A and F. Again, there will be 3 possibilities. The remaining ligands are B, C, D and E. We get like this. Totally, I get 15 possibilities. Since all the ligands are different, the complex will be optically active. For each complex, I will have its mirror image. So totally, I get 13 stereoisomers. These complexes and their mirror image. For understanding, let's try to draw this complex. Metal A and B, they are opposite. C and D, they are opposite. E and F, they are opposite to each other. So this is the complex. It is also possible to get mirror image that will be like this. This representation is applicable for both of this. Basically, they are mirror images. They are. Let's go for one more example. Metal is attached with. In that case, how many stereoisomers are possible? Opposite to A, I can have A. That is one possibility. Let's take that first. Opposite to A, I can have A. Opposite to A, I can have B. That is the second possibility. Opposite to A, I can have C. So that is the third possibility. In the previous case, I had 5 rows, but here I have only 3 rows. But the number of columns are same. The previous one I had 3, here also I have 3. Now let's arrange the remaining ligands. I have 2B, so opposite to B I can have B, and I have 2C. Here I go for BC and BC. BC and BC. Even if you go like this, you will get same BC and BC. Now you can compare these two. These two are same. So you can neglect one. Let's go for the next one. AB, AB and CC. The remaining 4 ligands I have arranged like this. AC and BC will be the other possibility. Again, AC and BC will be other possibility. If you compare these two are same. In this case, we are left with A, B, B and C. The other possibilities are here, these two are same. AC, AB, BC, AC, AB, BC. These two are same. So I can neglect one. So totally I have got 6 possibilities. Even though I have got 6 stereoisomers, all are not optically active. Among this, only one will be optically active. Try to find out that. Only one arrangement will have non-superimposibility and that will be optically active. That only can have enantiomer. The remaining thing will not be optically active. This is how we apply the Bayer's method to find out the total number of stereoisomers. You may be very familiar with some common complexes. Let us consider metal and A6. All the ligands are same. In that case, there is only one possibility and it will be optically inactive. Let us consider another complex like this, A4 and B2. 4 ligands are same and another 2 ligands are same. So in that case, we have 2 possibilities, that is cis and trans. This is cis complex. The other possibility is like this. Both are optically inactive. It has plane of symmetry, because of that it is optically inactive. Next one is metal A3 and B3. Again, two possibilities are there for this type of complexes. First one is facial. One phase of the complex will have same ligands. So now I have taken this phase that will have the same ligands. The another phase will have the same ligands. You can better understand in this way. In the middle I have metal. This is one phase. It is one triangular phase. The ligands whatever present in this triangular phase will be same. Similarly, the ligands whatever are present in this triangular phase will be same. So these three ligands are present in the backside triangular phase. So this is referred as facial isomer. The next one is meridional isomer. The ligands will be placed like this. So this is meridional isomer. Try to find out the total number of isomers possible with this type of complexes. Apply Bayer's method and try to find out the total number of stereoisomers possible for these complexes. The next part of this topic is configuration number. We have seen for the given complex there will be so many possible stereoisomers. Now the question is how to represent each isomer without giving the structure. Is there any simple method to represent the stereoisomer without giving the structure? Yes, we have. That is nothing but configuration number. Let us consider a complex like this. Metal is attached with some ligands like this. I have taken 6 different ligands, but it is not compulsory that all the 6 ligands should be different. Also, it is not compulsory that the stereoisomer should be optically active. The first step, we apply CIP rule and give priority. You may be very familiar with CIP rule. It is nothing but can encode per log rule. The same rule is followed here to give priority to the 6 ligands. Iodine has higher atomic number among the other atoms, so I give higher priority for this. The next one is bromine, so this will get the second priority. I have 2 Cl atoms, so they will get the same priority. After that, I have NO2 and pyridine. In both the ligands, nitrogen is attached to metal. So I go to the next atom. Here oxygen, but here I have only carbon. So this will get higher priority and this will get the least priority. This is the first step. Give priority to the ligands based on CIP rule. Second one, we have to fix the principal axis. It is nothing but the line that connects the ligand with higher priority, metal, and the ligand which is opposite to that. So this is the principal axis. Apart from that, I have a square planar complex here. If you don't consider the principal axis, what we have is a square planar complex. The third step, we look for the priority of the ligand that is opposite to the highest priority. That is, this is the principal axis, this has got the highest priority. Opposite to that, I have Cl, the priority of that is 3. So I take that number. Apart from that, I have a square planar complex. Here, I have priority 2, 3, 4 and 5. In this, the highest priority is given to Br. Now look for the ligand that is opposite to Br, that is Cl, that priority is 3. So this is the configuration number for this complex. So basically, configuration number is a 2-digit number that represents the arrangement of the ligands in the complex. Suppose if I go for a complex like this, in which both the Cl atoms are trans to each other. Let us consider a complex like this. Here both the Cl atoms are trans to each other. According to the rule, I have to give priority. That is the first step. This is the principal axis. Opposite to the first priority, I have priority 2. So the first digit will be 2. I have a square planar complex here. In that, the highest priority is given to Cl and the priority number is 3. Opposite to that, I have Cl, again the number is 3. So the configuration number for this arrangement is 2, 3. Let us consider a complex like this. The priority is given like this. Now, 2 ligands have got the highest priority. Which one has to be considered as the principal axis? In the previous case, I had only one ligand with highest priority. But in this case, I have 2. Which axis should be considered as principal axis? According to the rule, the opposite ligand which has the highest priority should be considered as the principal axis. Opposite to this, I have 3. Opposite to this, I have 4. So this axis should be considered as principal axis. Opposite to this, I have 4. So the first digit in the configuration number will be 4. Now let us consider this square planar complex. Highest priority is here. Opposite to this, I have 3. So 4, 3 is the configuration number. I go for one more example. Say I have 3 ligands with the highest priority. Already we have seen this should be the principal axis. Opposite to 1, I have 4. So the first digit in the configuration number will be 4. If you consider this square planar portion, now I have 2 ligands with highest priority. Whether I have to consider 2 or 3. Again, the rule is very simple. Opposite to this, I have 2. Opposite to this, I have 3. So according to the rule, the highest priority should be taken. So the configuration number for this particular complex is 4, 3. Let us go for few more examples. Try to find out the configuration number for these complexes. So try to find out the configuration numbers for these complexes. Finally, we are going to discuss the configuration for optically active metal complexes. In organic chemistry, we have R and S. Similarly, for metal complexes, we have del and lambda. So how to assign this configuration, that's what we are going to discuss. First, let us take a metal complex like this. Ethylene diamine is bidentate ligand. The structure will be like this. This plane is perpendicular to the plane of the paper. This line is the plane of the paper. This complex has no plane of symmetry and center of inversion. Because of that, this is optically active. This will be one enantiomer. The mirror image will be another one. To assign the configuration, we look into the molecule through this axis. When we view through this axis, these 3 nitrogen atoms will be in one plane, and they will form the corners of a triangle. I have taken this triangle now. The remaining 3 nitrogen atoms will form another triangle. They will be backside. They will be in different plane. Often the octahedral structure is represented like this. Now this nitrogen atom and this nitrogen atom, they are connected. This nitrogen atom is on the top. This nitrogen atom is at the bottom. So what I do, I connect this in this way. This nitrogen atom is towards us and this is backside. Similarly, this nitrogen is on the top and this is at the bottom. So I go for some type of wedge projection. Similarly, from here to here. I view the molecule through this axis. I place my eyes just above this point and view the molecule. When I view like that, these lines follow the clockwise direction. If it is clockwise direction, the notation is delta. Let us consider its enantiomer. First I take these 3 nitrogen atoms. They will be on the top. And these nitrogen atoms will be at the bottom. These two are connected. This is on the top. So I connect like this. Similarly, these 2 nitrogen atoms are connected. This is on the top. This is on the top and this is at the bottom. So I get like this. Now I view through this axis. The connection goes in the anti-clockwise direction. For this, we give the notation lambda. Now let us consider a complex with only 2 ethylene diamine. So only 2 bidentate ligands are there. Say also we have 2 more ligands. Say this is the complex. In the previous case, we had 3 bidentate ligands, so it was very easy. But here we have only 2. In that case, how to assign the configuration? First, we have to write this, the octahedral structure. In the middle, we have metal. Here I have 1 nitrogen and this is backside, so here I have 1 more nitrogen. So these 2 are connected. This nitrogen is here and 1 more nitrogen at the bottom. These 2 are ligands. This is the octahedral structure for the complex. I rotate this by 90 degree. I bring this nitrogen to the top. We are going to focus on 2 lines. The first one is this line where we have the bidentate ligand, and the other line is this one. We are going to focus on these two lines. These two lines should be on the top so that it will be easy for us to view. That's why I am going to rotate this complex by 90 degrees. So I am going to bring this nitrogen to the top. When I rotate, this will go to this position and this will come here. Since it is in the front, I give a thick line for this. What about this nitrogen? This will go to this position and this nitrogen will be here. The remaining two positions will have ligand. Now we are going to focus only this line and this line. For clarity, I take only two lines. If the thick line is towards your left hand side, the notation is lambda. Suppose if you get this towards your right hand side, then you have to give delta. Very often I get confused between this notation. I remember this way, L lambda. Let us consider the mirror image. Let us try to represent this, the octahedral structure. Now I have to rotate this structure in the anti-clockwise direction by 90 degrees. Since I have to consider this line and this line, I rotate this nitrogen by 90 degrees. So I have to bring this to the top. What I get is these two nitrogen atoms will be backside. I bring this to the top. So if you give numbering, say this is 1 and 2. Here this is 1 and 2. Say this is 3 and 4. This will be 3 and 4. I have rotated the octahedral structure in this way. Now I give thick line for this because it is towards us and this is backside. I consider only those two lines. Now this line is towards my right hand side, so the complex will be delta. Suppose, say you have complex of the type, here we have 6 different ligands. In that case, how to give the configuration? Say this is the complex and say this is the priority. The principal axis is here. You have to view the molecule through this principal axis. When you view through this principal axis, we will find only a square planar complex. B is here, C in this corner, D is here and E. 2, 3, 4 and 5. This is the principal axis. I view the molecule through the principal axis. Now connect the 4 priorities, 2, 3, 4 and 5. Generally, you have to start from the highest priority and to the one which is opposite to that. So I have to start from 2 to 4. And it has to go through the least number, so I have gone through 3, not through this. So here it is clockwise rotation. If it is clockwise, it is delta. Here I have one more example. Two ligands have the highest priority. Since this is the highest value, I take this as principal axis. I have to view the complex through this axis. I can find only this square planar complex. The priorities are given like this. Now I have to start from 1 and I have to go to 2. I have to connect the priorities. I start from 1 and go to 2. Here I have 4. The other side I have 5. Which route I have to take? I have to take this route because this has the lowest priority. So I have to follow this route, and it is clockwise and it is down. Often, if it is clockwise rotation, the configuration C is used. Anti-clockwise rotation, the configuration A is used. The first letter is used here.